So is my screen visible?
Yes, your screen is visible.
Okay.
Okay, so dear participants, session is ready to start. So within 1 minute or 2 minutes, we can start the session. Okay, so before starting the session, I just want to welcome Mr. Sridatta Jairam. So he is the student research scholar of Dr. Research scholar of Dr. Abhinav Kumar. So it's my great pleasure to extend a warm welcome to Dr. Abhinav Kumar. He is the assistant of professor in Institute of Artificial Intelligence and Data Science, IIT Ropar. So Dr. Kumar earned his PhD from IIT BHU and his specialization in artificial intelligence, medical imaging, deep learning, explainable AI, and trustworthy AI for healthcare application. He has published over 37 research papers in reputed journals, and he has received more than 1600 Google Scholar citations with an H index of 90. So we are privileged to have Dr. Kumar share his expertise with us. So on behalf of Electronics and ICT Academic MNIT Jaipur, I extended our sincere gratitude to Dr. Abhinav Kumar for accepting our invitation. So we are honored by Sir and look forward to an enlightening and enriching session. So, dear participants, it's great opportunity for us to uh, to attend the session by the Dr. Abhinav Kumar, but due to some work, he is a scholar, Dr. Sridatta, Mr. Sorry, Mr. Sridatta, he is taking a practical session based on the federated learning and the future scope of the federated learning. So, thank you very much for giving a valuable time to us, Mr. Sridatta, on the behalf of Dr. Abhinav Kumar. So very warm welcome to Mr. Sridatta for taking the session. So thank you very much, sir. Sir, now it's over to you, sir.
Thanks, sir. So I'll be presenting the session on federated learning code demonstration. So uh, to begin with, federated learning is a concept of distributed learning. So it is now in this notebook, what we are going to see is we are going to see the implementation of Fed average, which is basically a very first implementation of federated learning back in 2017, uh, which was implemented by in paper of McMahon. And then we are going to see how like the data distribution in the federated learning can be of different types, namely of IID, which means identically and identical and independently distributed, and non-IID, which is non-identical and independently distributed. And we'll be seeing some other algorithms in the federated learning, which will span across optimization, regularization, and personalization of the clients in the federated learning, and also representation, alignment, and distillation. And at the end, there is a table of federated of all the federated learning algorithms, where what directions like the research have headed into from 2016 to 2026. It has been prepared. And at the end, a discussion on advantages and disadvantages of each of those method, and how the literature addresses one over the other. So for this demonstration, we are going to use a digit dataset, which is basically 8 cross 8 image dataset, like a smaller form of MNIST dataset, which contains digit 1 to 10, and they are handwritten digits. And now coming to the introduction of federated learning. So what is federated learning? Federated learning is basically a scenario where we have all decentralized clients, a server client architecture in which we have our data is with the clients, but we have to make the server learn. So how will the server will learn without seeing the data actually which is belonging to the clients? So that is the core concept of the federated learning. And the uh, like the clients will have the models which will basically learn from the data and will send their learnings to the central server, and the central server will have its own model which will get updated basically from the updates across all of these client models. So to begin with, the objective function is defined for this. So the objective is to, there are two objectives basically. One is the overall objective. The overall objective of the federated learning is to make the central server learn basically from the learnings of the clients. So the client learnings is actually the local learning, and this local learning will have associated local losses, which will be dependent on the local data which is present inside the client. And this local client, whatever the learnings is being learned, which will, it will be directed to the server, and then the server will learn that. And basically when the server will learn that, and after that, there will be multiple rounds of learning in which after the server learns that, then that learning is again shared with the clients. So basically, indirectly, the learnings of each and every client will be distributed amongst the client themselves through the server without actually seeing each other data. So, well, coming to the first algorithm, which I first said, Fed average. So in this algorithm, it is basic implementation. What happens is there are multiple rounds which are denoted by T, 0 to T minus 1. This is a hyperparameter. And there will be a server. Server will have a particular model, and the initialization of that model in the beginning will be shared across the client. And in the first round, when all of the clients receive the initialization of weights from the server, the parallel training of or parallel learning of the clients will start. So, like each of the client, each of the K clients, whichever is are present, they will learn, and they will have a set of e-local epochs defined, and then basically they will get updated, and those weights will the model present in that local client, the weights of those updated weights of those clients will be shared back to uh, the server. Then what the server does is the server will get all the weights from the client, which is k different weights. Then these weights are averaged, and then those average weights will be updated in the updated to the weight of the server. So now when the server gets updated in the next round, again this updated weight of the server will be shared with every client. So indirectly, uh, epoch after rounds after round, each of the learning from the client will be shared with the server, and the server will again initialize those clients. So the all the data will be learned or trained locally. It will not be shared across. So the privacy is retained, but again, the learnings are distributed. So the data never leaves the client, and all the clients will have the learnings of what the data is trying to deliver the message. So now coming on to the implementation, what we have done is we have implemented like the dataset image digit dataset, and we have expanded it using augmentation, and we have kept the like the resolution, the data resolution of the data is 8 cross 8, and like the due to the data augmentation, the number of images are increased up to 8x. So now coming on to the code implementation, these are the header files. So the first header file like imports NumPy, which is basically used for mathematical or numerical operations in the training in the data. And the next one is matplotlib, which basically is used for getting plots, for getting plots or getting or displaying the output image or the image of the data set. And the next part is the sklearn. Sklearn datasets preloads the dataset, which basically this library has like the preloaded dataset in it. So in that we are importing load digits, and the next part next library is again a model selection. So in this we are using train test split. So what does train test split do is it splits the data set into training and test, basically depending on whatever percentage of test split that we are defining. And then we have other two libraries, which is copy and time. So copy is used for like copying the global model across. So as we are like initializing the weights again and again, and basically copying this server weights again down to the clients. So this copy library helps. And time is used for basically like clocking how much time it takes for building the data set or downstream tasks. So to begin with, we are going to initialize a random state with 42, which is a seed, which is a random seed for getting the reproducible result in this case, so as to initialize the beginning at the beginning in the server model. We are going to load the data here using load underscore digits, and it loads around 1797 images with 8 cross 8 resolution. And uh, we are going to load the images and the corresponding labels. So digits dot images will load the images, and whatever the corresponding labels will be loaded by digit dot target. And now what we are going to do is we are going to augment the data set. We are going to increase it. So basically for increasing, what we are going to do is we are going to apply this to augmentation, which is basically np.roll. np.roll shift the images by rolling the pixel from the corner sides. And clip is basically used to add a small Gaussian pixel noise. And we are also defining the clip range from 0 to 16. So after performing the augmentation, we are going to store all of these augmented images in the all underscore images and the corresponding labels in all underscore labels. Uh, After that, we are going to create the arrays, numpy arrays, which is basically x is equals to x and y, using all images and all labels. And why we are dividing it by 16 is to normalize it to 0 to 1. And the number of classes in this data set is 10, as it's a digit data set. And here in this y, we are creating another variable y, which basically has the one hot encoded version of the labels. So basically, if it is 0, it would have like one, it will be one hot encoded to 0 0 0 1 0 2, like that. And then is printing the statement like that we built the images so and so, and built it in this much time. And then we are going to apply the train test split. So what does train test split do is basically what I defined earlier is it is going to split the data set into train and test depending on the percentage of the test split that we have given. In this case, it's 20%, and the random state is 42 to get the reproducible split. And here we are going to define what's the dimension of the train. Uh, so x train dot shape is 64, and the hidden layer is the dimension of the hidden layer of the model, which is 64. And then we are going to plot the images. So for plotting, we are going to use the matplotlib library using I and axis, which is basically plots the images of these corresponding digits from 0 to 7. So we are going to run this cell. So now the data set has been built. The number of images, which was basically initially it was 1,797, is now 14,000 because of augmentation. And the uh, as we have defined the training and test split as 80-20. So the 80% of the samples will go for training, 11,500, and test samples would be 2,876, and the dimension of the images is 8 cross 8. So now coming on to the model part, we are going to like define here the client model and the core fed average functions. So initially what we are going to do is we are going to initialize the parameters for the central server and the model itself. Uh, and so for that, we are going to use this initialize underscore parameters function, which takes in the of input dimension of the model, or the input what we are giving. Since it's 8 cross 8, so it will be 64 dimension. And the hidden layer dimension is since we are going to use MLP model, so the dimension of the hidden layer inside the MLP layer will be the dimension that will be defined here. And the output dimension will be the number of classes, which is 10, and seed is defined as 0 here, that we can overwrite later. So now what it will do is initially it will first initialize np.random into R. It will initialize it with a seed, and then with that R, what it will do is, what we'll be doing is we will be defining this four parameters, which will be basically W1, B1, W2, and B2. and this parameters will be defined on the basis of the random state R. So R dot random input dimension and hidden. So this is a matrix. So so the matrix is defined with the initialized with the random state and with the shape as 64 cross the hidden dimension. Same for W2, and B1 and B2 being biased, we will be defining it as NP dot zeros. So now coming back to the variable parameter shapes, this variable like this will be storing the shape of the parameter tensor. And here we have another function of flatten, which basically what it will do is it will flatten the matrix into a vector so that we can do the operations, downstream operations. Uh, and again, unflatten will convert the vector back into the matrix for the parameters W1, W2. And now the next part is the softmax. Softmax is the last part wherein after like the last layer, the hidden layer, after the hidden layer, then we have to convert like the output, the 10 outputs that we get into, which is basically called as logits. We have to convert it into a probability distribution over 10 classes. So for that, we apply softmax, which is like the exponential operation that is applied, a normalization of exponential operation. And coming down, we have forward function. So forward function is where we like the model uh, operation of the model is. So what we have is like the four variables here: z1, a1, z2, a2. Z1, basically what it does is forward will be getting parameters and x. So in parameters, we will be having the four parts: W1, B1, W2, B2. And since this is a MLP model, so the Z1 will be the matrix multiplication of the input with the W1 parameter. And we'll be adding the bias here in the first layer. The output of the first layer is then passed through ReLU function. So ReLU is the activation function in between. And then we have the next layer, which is uh, the hidden layer. So hidden layer has its own weight of W2 and B2. So Z2 is the output of the hidden layer, and it again performs the output of the first layer A1 will be multiplied with the parameters of W2 and added with the bias of the B2. And then we'll be getting 10 raw logit scores. This 10 raw logit scores will then be passed through softmax. So this softmax will be giving us the 10 probability scores. Now, for the sake of federated learning operations, we'll be returning three uh, like outputs here, which is basically Z1. Z1 is the output of the first like layer, input layer, uh, but without the activation function applied. And A1 is with the activation function applied upon Z1. And A2 is the output of the last layer after applying softmax. Now coming on to the local train. So what does local train does is this is for training, as I said earlier, in federated learning, we'll be training our model locally. So in during training the model locally, there will be number of epochs that is being defined. So in this local underscore train function, what it takes is it takes the global parameters or the parameters that the client model is getting, and then the input and the output, the input sample and the corresponding ground truth, whether it is 0, 1 or 2, whatever label it is. And then the number of epochs for that like model to train, which will be defined, and the learning rate. batch size, and seed. Seed is basically like what initialization to be done for training, and initialization of the parameters to be done for training. And mu is like it is this we'll see like later on. This comes in another algorithm called as fed procs, where it is useful. So there we will see the importance of mu. So now for fed averaging, we will keep mu as 0. So coming on to the training part, what happens is first we will define a parameters. So basically whatever the server parameters are copied into the parameters of like the current local client model. So copy is the library that I defined earlier. It is useful here to copying the parameters. Now coming on to like we have defined R here for the random state, and we have defined N as the length of the training data. And now we are going to do the training. So for training based on the number of epochs, we are going to run the for loop. And for like doing the shuffling the training data, we'll be using the R dot permutation N within the batch. And now we will begin the training part. So what it does is it will we will apply the start in the range 0 to batch size, and then we will draw the data, which is the corresponding index from the X, which is the training data, and we will be drawing that index based on this IDX of start to start plus batch size. That is, we will be drawing that much amount of batch size of the data, and it will be based on this random initialization here, R dot permutation. And then the indices that are being drawn in that particular batch, we will give it to the input, like the training data that we are getting X, and then we will be drawing that data from the X particular location. X of B and Y of B will give us the particular input training data and the ground truth. And then here we will start like the operation, passing it through the model. So what we will do is we'll pass the parameters, that is we have initialized it like earlier, and the input xb, and we will pass it through the model, and this model will return us the three outputs z1, a1, and a2. And we will store the input length of the xb in m. And then what we will do is we will then start with, as we know the ground truth data here, we will start with the back propagation. So using the back propagation, we will like calculate what are the local gradients, and with the help of local gradients like dz2, once we have the local gradients, we will then move on to calculating the parameter gradients. So parameter gradients are dw1, dw2, db2, and db1. So as like when we apply this operation of back propagation, we will get the delta part of the update that we are going to perform in the model, uh, in the gradient update of the model. And then since we are not using this mu, we will skip this now. And uh, like now here what we will do is we will apply the update, which is theta is equals to like previous parameter minus the learning rate into the gradient update. So what it does is it will update the W1, W2, B1, and B2. Basically, based on whatever W1 and DW1, DW2, DB1, and DB2. And this updated parameters will be returned. Now, for each round after like after the training is completed, or the entire federated learning is completed, Then like if we want to see what's the accuracy, then we can perform this. So for accuracy, we'll be passing again the input and the ground truth, and this forward function again is the model here, and we'll be passing parameters in the input. It will return us the softmax output, and then we'll be checking whether it's matching with the ground truth, and we'll calculate the mean that will return us the accuracy. Now coming on to the Fed average part. So this is the like the algorithmic like implementation. What it does is it takes into uh, input the parameter list and the weights. So parameter list are the list of parameters W1, B1, W2, and B2, and the weights are the like what is the weight in each of the like the client. So what we will do is we will first sum the weights using sum operation, and then we will define the average as a dictionary. So now what happens here is we will run this for loop across all the parameters that are being defined, parameter list. So this parameter list being defined for each client will give us the weights associated for the each client, and then this weight associated with the each client are then being added or stacked, and then the average is computed, and then this average is then used for like updating, or this average weight is the weight of the server. So it's like calculated over each of the weights W1, P1, W2, and P2. So this is was the implementation of Fed average. Now we will run this. Okay. So now next part is like we will be simulating the client with the IID partition. So these are like quite a few hyperparameters of federated learning. So number of clients is n underscore clients is number of clients. So number of clients is the like for a federated learning, how much number of clients are there. So here we have defined it as 8. So 8 is the number of clients now. We will have a server and there will be 8 clients. Now the rounds is the number of like the number of updates the server or the weight update that will be done with the server. So like 15 number of weight updates will be done with the server. Local epochs is the epoch that is done locally, or the training of the client that will be done locally. So here we have defined local epoch as 1. So now coming on to running the Fed average function. So here this function takes the input of client IDs, basically the IDs of each client, number of rounds, or the current round, or the total number of rounds that the federated learning has to take place. Local epochs, like how much number of training is to be done for each client, and the learning rate, and the seed offset, and the mu, and the verbose, that if you want to print like the date after each round update. So now what happens in the start is we will define a variable called as global parameters. We will initialize it with the seed that will be the server's starting global model. And we will create a history list that will store the history of each rounds. And there will be client history. Again, this will store the history of the client of local epochs that is happening in the client. And now we'll begin with the rounds. basically the federated learning. So what happens here is we will define it in the for loop, and it will run in one iteration at a time. And then we will define this variables, locals, sizes, round client, and round client accuracies. So now to begin with, what we will do is we will start for that, like after entering one like this beginning round, what happens is we will then run the for loop for each of the clients. So like beginning for the first client, what it will assign the first client as C and its specific client ID. And then what it will do is it will start training the client. So the training function which we have defined earlier as local train, and this will take input as the global parameters. So initially the global parameters are randomly defined, so that will be like copied into the training of like the global parameters will be copied into the training of the local client. And then the particular data for that like for that local client, X train of CIDX will be like the data for that particular client, and the Y train will be the data for that particular ground truth data for that particular client. And the local epoch will be the number of training epochs that will happen in that client, and the learning rate will be defined by LR. And again, the seed will be defined by seed offset. And now coming on, we will get like the updated parameters of that particular client in LP. And then we will have client accuracy. So client accuracy will then like we'll be passing whatever parameters that we got, accuracy of LP, and then we will have X test, that is the test data for that particular client, and Y test that particular client, and this will measure the accuracy of the client accuracy. Now, like after that, we will update the variable of locals. So locals will actually store the local parameters, and sizes will store like the what was the length of the client, or what number of clients are trained, right? And the round accuracy, client accuracy will store like how much number of uh, client are being trained, or what was the accuracy of the client accuracy, average client accuracy of the particular round. And after that, we will print the verbose of what was the round and what was the client and what was their local accuracy and what was the number of samples. Then the client history will update all the round client accuracies, and the global parameters is then computed after the training is done for the entire the training is done for the entire clients. The average of weights will be done, and then that will become the weight for the central server. And then as now we know the weights of the central server, so now we will pass these parameters of the central server through the accuracy to basically calculate what will be the accuracy of the global like the server on the test data. So this will give us the server accuracy. So now after that, we will then update the history into the server accuracy, that it will store these like historical history of all the accuracies of particular round of the server performance of the server model. And then again, we will print the verbose of the particular route and the particular server accuracy. And after entire operation is done, this will return us with, like, after all the rounds, what was the global parameters and what was the history, like the server history, and what's the client history. And now these are like some of the operations that is done before beginning, like applying the federation learning, that is having the IID data. So what does IID data do is, IID data is basically independently and identically distributed. So since our class is like the class of the data is 10, number of classes is 10. So in IID data, the distribution of the data in each client should have 10, like the distribution of the data in each client should be similar. The class distribution should be similar. So for that, the split is performed using RNG dot permutation based on length of the training data and the number of client. Basically, it shuffles all the training indices and then cuts them into 5 equal chunks, or 8 chunks in this case. And we will be printing the Fed average on like we'll be printing the running of status of running of Fed average on IID clients, and then we will like run the Fed average algorithm here based on this IID data that we obtained, and we will enable the verbose is equals to true. That will give us like what's the update for particular round, and what is the client accuracy and server accuracy. And then we will go on with the plot. So this plot will plot basically what's the accuracy plot after each across rounds, and basically the test accuracy, and it will plot for even the global server and as well as the client. We will run this. So we have given this for the 15 rounds. So beginning at the beginning round, like all the clients were having the accuracy of 52%, 42% range, like 50 and lowest being 38. And our server had the accuracy of 60%. Then like this after one round it improved to 75%, and the local accuracy of the clients also improved by like 10%, almost 64 54. And then after at the end of 15 round, we are ending up with the server accuracy of 94%, and the client accuracy, well, it's headed down to 88 and 90s. So the final Fed average, like the updated weights, were having this test accuracy of 94.09%. And this is the graph for IID setting. So this is the server update. So server, like the performance of the server was well ahead of the each of the clients. So each of the clients has the update, oscillating update, while the server, like having the view of all the client, like got the performance higher. So now coming on to the real world case. So in the actual scenario, there will not always be IID clients available, because like the clients may have certain skewed data. So so as to see in that particular case what happens if we do the federated learning. So, like example would be a hospital where, or a phone where data is extremely skewed because of some rare disease or personalized data. So in that case, how the centralized model would work. So here I'm using the term upper bound reference, which is basically what I'll be doing is I'll be training a separate server model on the entire client data to see what is the upper performance the model can reach with that whole training data. So now coming on to like how do we generate this non-IID data? So what we do is we create a skewed partition, and like the theoretical implementation is we cut like the parts into, like we'll divide it into 2n clients, and we will create the shards of data, which is basically a group of data with almost two classes, and like two classes max, 1 to 3 digit classes, and it will omit like the balanced mix of all classes. So this starts with the random implementation with random state. Then we like define the order as np.arcsort, that will basically sort all the labels of the ground truth, and then shards of data is created based on the number of clients, and this number of clients is multiplied by 2, so that there would be 2 in number of contiguous uh, data or pieces, and then this data, like the shards of data, is then assigned to each of the clients. So in this case, what happens is each of the clients would end up with two shards of data concatenated together, and they would end up having like the two classes, which is not a independently or identically distributed, because each of the server will have different classes. So now to like generate the data, we'll like call the function non-IID split. There we'll be passing the ground truth data of the training data, and the number of clients here is 8, and the seed as 7, and then we'll print the status. And then what we'll do is we'll run the fed average algorithm on this non-IID data, and we will enable the verbose status to be true to see what's the status of after each round. And then we will get this parameters of the server using gp underscore non-IID, and we'll also get like the accuracy of the server using acc underscore non-IID, and we'll get the client history using like the client underscore historical. So now like to also have the implementation of the upper bound. So what we will do is this like we will train our server model on this data. So like what we will do is we'll create one model. We'll pass the entire training data to this model to basically see like what will be the accuracy if the server model is exposed to entire training set data. So that becomes the upper bound, and then we will calculate like what is the accuracy, and then we will print what's the like accuracy after each number of epochs. So now this is like we'll print what's the accuracy after performing the fed average on non-IID data, and then what is the upper bound of the server or the highest accuracy that the model can reach using training exposing the server model directly on the client's data. Then we will plot this the curve. So this curve will have like the rounds, client history, basically what's the accuracy after each round, and this like this plot will be on non-IID data, and also we'll also be plotting what's the round and what was the like performance for when it was with the like centralized or upper bound, and on the IID and non-IID for comparison. We'll run this. So for the non-IIT data, uh, the training begins with the local accuracy of 18% to up of 31% accuracy, and the server accuracy was 33%. And then it reached in the next round, the server accuracy jumped to 44%. Likewise, it improved, and in the 15th round, the server accuracy was 83.69%. And for the comparison of the centralized epoch or the upper bound, uh, the upper bound accuracy was 96.2% to 1%. So clearly, the data distribution matters in federated learning. So if the data is not identically and independently distributed, then the performance of the server model will be severely affected, and it will not reach its full potential. So this graph also tells us how the learning took place. So in this non-IID setting, this client's local learning curve versus the server, like the global curve. So what happens is the due to the local data, the server actually or the client accuracy actually fluctuated, and it never crossed above 40%. But uh, so, somehow the server having a indirect view of all of this data and getting update across this data, the performance improved up to 83%. But as the upper bound accuracy was 96.21%, this accuracy, the accuracy that was reached by using this non-IID data did not translate into actual upper capacity that the server model can reach. This fluctuating data here actually affected the server model, and it actually remained within 85% of accuracy. So this is the comparison between like how the data would influence when the distribution is different. This is the graph on the upper part, bluer part represents what is the upper bound, or what's the maximum potential of the model that we are training can reach. Well, it's up to 95%, 96% that we saw earlier. And the Fed average algorithm using IAD clients clearly has clearly drove up till that. But when we did the when we changed the distribution to skewed distribution, then the Fed average algorithm was not able to catch up with that performance. So this clearly shows how important it is that the data across the clients, and how important it is, and how challenging it is to solve this problem of skewed data in the federated learning scenario. So now coming on to the next part, we'll be discussing the foundational federated learning variants. So we have FedProx algorithm and the differential privacy Fed average algorithm, and then we'll be seeing how local fine tuning would perform in the Fed after performing the Fed average algorithm, and what happens when there is only a partial participation of clients from the Fed in the federated learning scenario. So now coming on to the FedProx algorithm. So FedProx algorithm, what it uh, solves is basically different uh, what uh, what scenario if each of these local clients has different device speeds, and it has different it can train for different epochs, or basically if it has different capabilities. The capabilities is not similar, is what it is trying to solve. So how the solution is introduced is, along with the objective, they're introducing another regularizer parameter of hyperparameter mu, and the weights are regularized using w minus wt, and they're squared. So what this extra quadratic term does is, it tries to it tries to hold the clients to not drift too much, so that this the client and the server drift, or the update which is happening in the server and the updates which are happening in the clients remain very less. So this delta f plus mu w minus wt in the SGD step, in each of the clients, this update translates to this form. W minus W means W is the current date, or the current parameter, and W is the previous parameter weight and learning rate. And this initially the gradient would now would be added with an additional parameter of mu to control the drift of the parameters across the weight updation. So in a short overview, how does this fedprox works is, initially we will have the weight, and while updating the weight, we are introducing this mu, and this mu uh, will again calculate what's the drift in the weight with the previous weight, and it will multiply mu, so that there is a damping effect of the weight that's happening. And then again here, no change in server aggregation. The Fed average algorithm continues as it is, like what's happening in algorithm 1. So mu is equals to 0 is exactly the Fed average. And what happens when the mu's are changed, that we are going to see in the implementation. So what is the function is, we will have this run heterogeneous. So we will have client IDs, and we will have this client epochs. So why client IDs and client epochs? Because as I discussed earlier, each of these clients have different epochs because of their differing capabilities. And by default, mu is defined as 0, but while calling the function, we'll change and see what's the scenario. And number of rounds will be 15 that we saw earlier. And seed offset would be what's the seed. And track drift would be like how much amount of drifting is happening. So now what is happening is, we'll begin with the initialization of the parameters. We will then initialize also few variables here, accuracy history and drift history. And then we will start with the rounds. So in rounds, we will have this some of the local variables to store the history after rounds. And then we will for each round, we will be performing the local train that we saw earlier in Fed average algorithm. Uh, Everything remains the same apart from mu. So mu would be defined, like we will change the mu based on whatever we are giving while calling this function. And then like if we have enabled track drift, so then we will add this L2 distance. So this L2 distance is basically what we have defined here W minus WT is flatten LP minus flatten GP. That is the earlier update versus now the current update. And then we will store this like the local parameter in LP and sizes of number of clients in that particular round in length of CIDX. And then we will also store what's the drift of the what is the drift of the uh, drift of the client uh, using drift underscore history. And then we will calculate the mean of the drift. And then in the end, we will be updating our Fed average with the locals or the local parameters that we got using LP. And then after averaging all of those, that will be stored in GP. And then after that, we will be calculating like what's the accuracy. And in the accuracy, we'll be passing the, this is the server accuracy. We'll be passing it through GP and through the test data of the clients. X underscore test and Y underscore test is the ground truth. Then after that, this would be returning us with the GP accuracy history and the drift history. Now, for client epochs, we have defined like 1, 1, 5. These are the varying client epochs. Like first client has the capability to run only one epoch, second has one, third has five, like that. And we will be running this algorithm using different mu values, which is mu is equals to 0 and mu is equals to 0.3. And then we will be printing all like what was the drift across 0 and 0.3 and what was the corresponding accuracy. And then we will be plotting them here. So the plot would be with weights, the drift, drift versus the like the number of rounds. We will run this cell. Okay. So now for like when the mu was equal to 0, then we applied Fed average algorithm. So then the drift was 4.338. And then we applied a Fed prox algorithm. When we applied mu is equals to 0.3, then the drift was like 1.39. So the final accuracy was Fed average using the Fed average algorithm. We had a final accuracy of 87.80. And after applying the final accuracy, after applying the Fed prox, the accuracy actually reduced to 55.74. So here, after like applying the Fed prox algorithm takes a hit on accuracy, but the drift across the clients or the clients will be more of like the clients will now have more like the weight distribution would be similar to the server weight distribution. But like because of this, because of like having this distribution similar to the server weight distribution, there is a trade-off in the performance of the model. So now this is the graph. Like using Fed average, the client drift would be the graph of client drift would reduce, but it would be higher than the Fed prox algorithm which we applied. So tuning of the Fed prox algorithm is also a must because it acts like a regularizer. So like if we apply proper tuning, then we can have a trade-off which like we will be having a trade-off where we'll be having accuracy as well as better accuracy and better client drift. So the main challenging part of FedProc's algorithm is it tries to reduce the client drift under like when there is a heterogeneous computation. Now coming on to the next algorithm, which is the Fed differential privacy. So what does this algorithm say is uh, like when this training happens across the client and the weights are being shared to the server, can this server leak, or can this update leak information? So there are methods such as gradient inversion or membership inference, which can basically retrieve or the leak the information to the server of what kind of data the client has. So it's basically trying to address the privacy of the data in the clients. So here to solve that, the two mechanism is applied. So basically, first, what is done is first the L2 norm is applied, like the delta k, the updates are multiplied with the minimum of 1 comma c by delta k, and this is the clipping part, and this can have the L2 norm, the capping of the L2 norm is done to a constant of c. And then after this like the capping, then slight noise is introduced, and this noise is defined with the noise multiplier z, and it has like again constant c is used for as a variance z square c square I. So what happens here is by introducing a noise in this, the noise and clipping, the weights of uh, the weights of the clients that are being shared with the server uh, cannot be used for retrieving the information. So this like has a privacy preserving part of client updates. So now coming on to the implementation, like we have defined the function as differential privacy, DP fed average round. So this goes on round after round with each of the client IDs, and there would be like for in a round, like we'll be doing this local train, and after local train is performed, then the difference in parameters is stored in delta, and then the normalization is applied on this delta, and then if it is checked if the norm is greater than the clip underscore norm, so the clip underscore norm is given as 5, then this delta is multiplied by clip underscore norm, and it is then divided by norm, and then whatever the updates are, it is updated into delta. Then in the average update, uh, the mean is applied over this updates, and these updates are the clipped updates. And then after for this clipped updates, then a noise is introduced using random.normal, the normal noise, and then the particularly this part with the variance, like noise multiplier into clip norm divided by length of client IDs would be used to have the variance, and then the new noisy or the noise introduced parameters are then like uh, are then stored in this new underscore flat, after applying flatten on the global parameters and adding this average update and noise. And then this new update is then unflatted and returned back. So now after that we'll be running this Fed average or the differential privacy Fed average algorithm. So initially it begins with the global parameters, and we'll be initializing parameters with randomly, and then it will begin with rounds, and after round, we will be calling this dp underscore fed average round, and then we'll be passing what would be the global parameters or server parameters, and what would be the client indexes that would be training for that particular round, and what is the clip now, and the what would be the noise multiplier, and what would be the seed. And then we will be storing the history, uh, and this history will contain actually the uh, accuracy of that uh, particular server on the test data of that particular route, and then we will be returning the global parameter and the history. Now we will be doing this for differing noise levels: 0, 0.5, 1, and 1.5. So 0 is there is no privacy, no noise at all, while 1.5, like 1.5, else that we are introducing noise in it. Then we'll be running the dp underscore result, and it will be called using dp underscore result will store the result for this differing noise levels, and we'll be passing this differing noise levels through the run underscore dp underscore fed average. And then we'll be plotting this, and this plot will have like what are the accuracy, and like correspondingly what type of noise we have introduced, and after introducing those noise, what would be the differing accuracies that we get for that particular like updates in the server. So now we will run this. Okay. So now again here we have like when there was no noise, then the accuracy was higher. When the noise was introduced, the accuracy fell, and as we went on introducing more parameters of or higher parameters of the noise multiplier, then there was a drop in accuracy. Again, this is used for preserving the uh, the information of the client. So there again should be a necessity of a proper hyperparameter tuning of this noise multiplier, because if we increase the noise amount of noise in the parameters, then the information would be like the noise would be dominating the information. So with the proper parameter tuning, we can get like proper privacy preserving part, as well as the like uh, good accuracy also. So now coming on to the next part is naive local fine tuning. So here what is done is, firstly a like uh, if like here the main part is why this naive local fine tuning is in the case of personalization. So personalization is ability for servicing different clients with the higher or better better version of the model. So what it is done is, firstly, the federated algorithm is applied, and after all the rounds have happened, then the server model is shared with all the clients. Then after all of this, then a particular uh, fine tuning is done at the end. So this model is then again trained on the each of the client's data, and this training uh, creates a different personalized model for that particular data. So here again it improves personalization, but like the hit is where it takes the hit is there, the model would be like drifting, the client models would be drifting away from the server model. So because of that, uh, like the accuracy or the drift in the client and the server performance would be higher because of this. And the client's skewed distribution also would impact. So for implementing this, what we will do is, first we will create this client validation split. So, like here, what we will do is we will at least held one sample out for validation in each of the clients, and then in this client, training and the validation data would be separated. And then after the each of the client will have the training and validation, then we will run the Fed average algorithm on the training data that we newly created, or that we divided. And then after that, uh, the after like after running the Fed average algorithm, then what we will do is we will do the fine tuning. So here in the fine tuning part, we will again go through the number of clients in this for loop, and then we will apply the local training, and then we will like see the accuracy of this model on its own data, and as well as the other test data, to just have a view of how like how much drifting has taken place. So we will run this, and then we will like print what would be what was the global mean accuracy and what was the personalized accuracy average. So like after performing the fine tuning uh, on its own validation set, the accuracy was 98.1%, while this particular model of client zero, that personalized model, had only 31.6% on the global test data. So, like if we see after personalization, uh, the there was a good improvement on the local test data, but globally the model was performing poorly. So when like the we calculated like what was the mean accuracy. So on its own, the global accuracy was 81.8% on its own data. But when like on its own distribution, the personalized was 96.9. This was for server. But when we implemented it for client, the accuracy fell down to 36.3%. So if we go for fine tuning the data set, then the performance of the data would uh, come down because of the drift in the data. So uh, like creating solution or solution solving one part of personalization actually creates the problem in the implement or creates a problem in the performance of the global model, or it drifts the local model away from the global model. So this was one of the implementations. And then the second, the another part is partial client participation. So this is the scenario when not all clients participate in the federated learning. So in this scenario, then again there is a trade-off. So this is again linked to a real-time scenario. So whenever like a model needs to get trained, there would be in a federated learning, there would be issues like the particular client may be down because of issues in devices or issues in its availability. So for that, we'll be simulating that. So what we will do is first we will be like defining what is the number of clients here, 20, and then we will be dividing the data in an IID form and in a totally randomized way of uh, allocating it. And then we will be running the Fed average algorithm, and then like using the Fed average algorithm here, the catch is that we will be simulating the number of like the availability of clients. So this availability of clients is actually controlled by this client indexes. So and the C is the number of clients that are available. So percentage wise, we'll be simulating it. And then for those number of clients, we'll be performing the Fed average algorithm. And then like the Fed average algorithm will result in global parameters, and then those particular histories will be saved, and then those histories will be returned back. So, and then coming down, we'll be plotting those things. So, we'll be plotting like after all running the Fed average algorithm on that, what was the plot? And this is the plot of like the test accuracy against the number of rounds. And again, like what was the effect of the client participation? So, we'll run this. So C is equals to 1 indicates full participation. So when there was full participation from the client, the global accuracy of the server reached up to 88.94. And when there was a reduction of client by 50%, then this final accuracy reached up to 88.21%. And then when the number of clients fell down to only just 20% of the entire pool, then the final accuracy was 87.59. And this graph shows that. And it also shows how like the client availability also shows how drift, like how much performance can like vary. So there is a lot of oscillations here while like improving the performance. But when we see for entire client, the climb of the accuracy is smooth. So now coming on to the other federated algorithms, we'll be seeing again the next algorithm. So the next algorithm that we'll be seeing is Fed average M or Fed Adam. This is actually a adaptive federated optimization algorithm. So what it does is it
Sridhar,
is, yes,
yeah, let's just first let me explain federated learning in medical setting, then you can continue, okay, after that.
sure.
Dear participants, Dr. Abhinav, Abhinav Kumar is now going for taking a small lecture based on the Medisec federal. So that is based on the medical science. Okay. So now I have already introduced to Dr. Abhinav Kumar, but I wish again I extend a warm welcome to Dr. Abhinav Kumar. He is an assistant professor in School of Artificial Intelligence and Data Science, IIT Ropar. So Dr. Kumar earned his PhD from IIT PHU, Varanasi, and he specialized in artificial intelligence, medical imaging, deep learning, explainable AI, trustworthy AI for healthcare application. He has published over 37 research papers in reputed journal and has received more than 1600 Google Scholar cited with an H index of 90. So today we are privileged to have Dr. Kumar share his expertise with us. So on the behalf of Electronics and ICT Academy MNIT Jaipur, I extend our sincere gratitude to Dr. Abhinav Kumar for accepting our invitation. So we are honored by your presence and look forward to an enlightening and enriching session. So thank you very much, Dr. Abhinav Kumar, for giving a valuable time for us, MNIT, EICT, and all the participants. And also thanks to Mr. Yes, I forgot the name, Siri Reddy. So thank you very much, sir. Now you can, I over to
Yeah, yeah.
you.
Thank you, sir, for the nice introduction. So first of all, I would like to thank the organizer of the Faculty Development Program and the EICT Academy for inviting me. So today I'm going to discuss Medisec PET, which stands for Private and Secure Medical Image Classification in the presence of medical clients. So this work basically combines three important research areas, that is medical image analysis, federated learning, and privacy preserving artificial intelligence. So before I explain the proposed method, let me ask you a simple question. Suppose AI researchers from 100 hospitals want to build one powerful deep learning model for disease diagnosis. So what is the first requirement then? So obviously we need data from all these hospitals because deep learning models become better when they are trained on large and diverse data sets. Okay, now comes the practical problem. Can hospital simply send all its patient data to hospital B or to a cloud server? The answer is no, because medical records are highly confidential and are protected by privacy regulations such as HIPAA and GDPR. So, although hospitals want to collaborate legally, they are not share cannot share patient data. Okay. So to solve this problem, researcher introduced federated learning. So the basic idea is very interesting. Instead of moving the data to the model, we move the model to the data. Okay. So every hospital trains the model locally and send only the updated model parameters to a central server. So initially what we are doing, everyone believed this completely solved the privacy problem. But later researcher discovered another issue. Suppose if patient images are never shared, the model parameter themselves can leak sensitive information. Why? Because using techniques like model inversion, a attacker can recover information about the original training images. So similarly, if one participating hospital behave maliciously, it can position the global model by sending incorrect weights. Okay. So our questions become, can we design a federated learning system where neither patient data nor model parameters are shared? So this question motivated our research for this work, Medisec Ped. So in this presentation, I will explain how Medisec Fed solve the problem using knowledge distillation and model inversion instead of exchanging complete neural network parameters. Client exchange only prediction logics computed on synthetic images. So this makes our framework more secure, more communication efficient, and more robust against malicious clients. So agenda is like, first we discuss the motivation. We will understand why collaborative learning is essential in healthcare and why traditional centralized deep learning is not feasible due to patient privacy and legal regulation. Next, I will introduce background concept before understanding MediSecPed. It is important to understand three fundamental issues like federated learning, knowledge distillation, and model inversion. So let us first understand the real world problem. Why is the medical data so valuable for AI? And at the same time, why it is so difficult to use for collaborative model training? So let us understand the actual problem that motivated the research behind MediSecPed. So before proposing any solution, it is important to understand like why existing approaches are not sufficient. Okay, so as you see on slide, there are four major challenges in developing AI models for healthcare. So first challenge is fragmented and private data. So it is like, for example, one hospital may have thousands of chest X-rays, and another hospital may have specialized in brain MRI scan, and other may have histopathological images. So no single hospital have sufficient diversity to train a highly generalized AI model. So as we know, deep learning models perform better when they are trained on large and diverse data sets. So therefore, collaboration among hospitals is highly desirable. Second challenge is strict privacy regulation. So now suppose these hospitals decide to combine their data set. Can they simply upload patient records to a central cloud server? The answer is no. So medical records contain highly sensitive patient information and are protected by privacy regulation such as HIPAA and GDPR, and various national healthcare policies and regulations are there. So therefore, hospital cannot legally share patient data with external organization. So this become one of the biggest barrier in developing collaborative AI models in healthcare, especially. Okay, so third challenge is high stakes error. So now researchers are proposing federated learning model as a solution because the hospital no longer need to share raw patient data. However, there is another important issue. If hospitals share only model parameters, those parameters may still leak information about the training data. So researchers now they've shown that using model inversion attacks, an attacker can reconstruct images that reassemble the original training samples. So in healthcare, it is a serious privacy concern because even partial reconstruction of patient information is unacceptable. Fourth challenge is hostile participant. So if we consider like the possibility of malicious clients. So federated learning assumes that every participating client behave honestly. But in practice, one or more clients may intentionally send manipulated updates to the server. So this is known as model poisoning or backdoor attacks. Okay, so such attacks can significantly reduce the accuracy of the global model or even force the model to produce incorrect prediction for specific inputs. So in healthcare applications, an incorrect prediction may directly affect patient diagnosis and treatment. So now that you understand the challenges, let me first understand how classical federated learning works. So on the basic workflow is very clear and you have also seen the demonstration. It is will be very easy to understand how MediSec-Ped works, improves upon it. Okay. So as you see in this figure, we have a central server. Okay, and a multiple participating hospital has its own private local data set, and this data set never leaves the hospital. The training process begins when the central server initiates a global model. This could be a deep learning model such as maybe ResNet, DenseNet, EfficientNet, depending on the application. Okay, those are server then send this initial model to all participating hospitals. So now each hospital trains the received model locally using its own medical images. Okay. Since training happens within hospital, patient privacy is preserved because medical images are never transmitted over the network. So after completing local training, the hospital do send their data sets back. Instead, they upload only the updated model parameters or gradients, which are represented by symbol theta. You can see in this figure. Okay. So the server collects model updates from all participating hospitals and combines them using an aggregation algorithm, mostly federated averaging or FED-AVG. Okay. So in simple terms, server computes the weighted average of the parameter received from all clients to produce a improved global model. Okay. So this updated global model is then sent back to all hospital, and the same process is repeated over multiple communication round until the model converges. So the federated learning cycle consists of mainly 4 steps. So what will be those steps? First will be the server distributes the global model. Second, each hospital performs local training. Third, hospital send updated model parameters to the server, and last and fourth one will be the server aggregate these parameters and create a new global model. So this iterative process continues until satisfactory performance is achieved. So after first glance, this appears to be an ideal solution because the patient data never leaves the hospital. However, there is one important question we should ask ourselves. Are model parameters really safe to share? The answer is no, not always. Although patient images are not transmitted, recent research has shown that model parameters themselves can leak information. An attacker can analyze these parameters to infer sensitive information about their training data. Okay. So if malicious clients upload manipulated model updates, the entire global model can be corrupted. So while federated learning successfully solves the problem of data sharing, it introduces new challenges related to model privacy, security, and communication costs. These limitations motivate the need of a more secure collaborative learning framework, which we exactly called and what Medisec FED proposes. So moving like classical federated learning has real weakness. So now we understood that the workflow of classical federative learning. Let us discuss why it is still not sufficient for sensitive applications like healthcare. Although federated learning keeps the patient data local, it introduces several security and practical challenges. Okay. So let's discuss one by one. First one is model poisoning. So in federated learning, the central server assumes that every client behaves honestly and sends genuine models updates. Okay. So, but what if one client is compromised? Instead of sending correct model parameters, the malicious client can unintentionally upload manipulated or noisy parameters. Since the server aggregates update from all the clients, these malicious updates become part of global model. Okay, so as a result, the performance of the global model degrades, affecting every participating hospital. So the security of the entire system depend on the honesty of the participants, participating clients. So then second one is uh, backdoor attacks. Okay, this is even more dangerous because the global model may appear to perform normally during testing. However, when a specific trigger is present in the input image, the model intentionally produces an incorrect prediction. For example, if we can take an attacker may train the model so that whenever a tiny artificial pattern appears in a medical image, the model misclassify the disease. Okay, since the trigger is hidden, such attacks are difficult to detect and can have serious consequences in clinical decision making in healthcare. Third challenge is model inversion. So many people believe pediatric learning is complete private because patient data is never shared. but the privacy is not guaranteed simply because the data remains local. So researchers have shown that attacker can analyze the share model and reconstruct information that resembles the original training image. So in medical application, even partial reconstruction of patient information is unacceptable because it is violates patient confidentiality. So although raw patient data is protected, model parameters themselves can become a source of privacy leakage. Then other weakness is communication cost. So modern deep learning models contain millions of trainable parameters. For example, like you see in ResNet model, which may require transferring tens of megabytes of parameter during every communication round. Okay. So now imagine 100 of hospital participating in federated learning. The communication cost becomes extremely high and often becomes the bottleneck rather than a computation itself. So this increasing training time and makes deployment difficult in bandwidth constrained environment. So there are two key ingredients of Medisec PET. Okay. So how hospital can collaborate without sharing model parameters? The answer lies in two important techniques that forms the foundation of Medisec PET. These are knowledge distillation and model inversion. So let us first discuss knowledge distillation. Okay. So knowledge distillation, is a technique where one model transfers its knowledge to the another model. Traditionally, we can call the larger and well-trained model the teacher and the smaller model the student. Okay. Instead of learning directly from the original data set, the student learns by mimicking the teacher's prediction. So now what exactly is transferred? It is not the model weights, it is not the training data, only the output logics, that is, you can say the prediction score before the softmax layer are transferred. So these logics contains much richer information than the final class level because they tell us how confident a model is for every class. So for example, if image belongs to pneumonia class, the teacher may assign probabilities like 90% pneumonia, or you can say 8% normal and 2% COVID. So the student learns this complete probability distribution rather than only the final label. So this makes learning much more effective. Then you may ask another question. Knowledge distillation usually requires a common data set. But in healthcare, obtaining a publicly labeled medical data set is extremely difficult. So this is where data-free knowledge distillations become important. So instead of using real medical images, we generate synthetic images that are sufficiently representative for knowledge transfer. So this eliminates the dependency on expensive public data sets. Okay. So then second component is model inversion. So model inversion is used to generate the synthetic data sets required for knowledge distillation system. So the process begins with a publicly available pre-trained model. We do not use any private patient data. Instead, we start with random noise as the input. Then using the deep inversion algorithm, we iteratively optimize this random noise. Okay, the optimization forces the generated image to match the batch normalization status learned by the pre-trained model. So after several iterations, the random noise gradually transforms into a realistic looking medical image. Okay, so these generated image resemble real medical images such as chest X-ray, but they do not belong to any actual patient. So therefore, patient privacy is completely preserved. So now the next question in your mind maybe arises, why combined knowledge distillation and model inversion? So let us understand these two, why these three techniques are combined. So model inversion provides the synthetic data set. Knowledge distillation uses this synthetic data set to transfer knowledge among hospitals. So as a result, hospital never exchange patient data. They never exchange model parameter. They exchange only prediction losses computed on synthetic images. So this simple idea solves multiple problems simultaneously. It improves privacy, reduce communication overhead, support heterogeneous client models, and makes the framework more robust against malicious participants. So from this slide, you can say the key takeaways are like model inversion generates synthetic data, and while knowledge distillation transfer knowledge using only prediction logic. Together, these techniques eliminate the need to share both patient data and the model parameters. So this is the core innovation behind MediSecPet. So now this is the heart of our paper Medisec PET. This is the overall diagram. So everything we discussed so far, the limitations of predictive learning, knowledge distillation, and model inversion, which comes together in this architecture. So although this figure looks very detailed, if you see, if we follow the number steps from 1 to 8, okay, one by one, it becomes very easy to understand. So step one is model inversion at the server. You can see in the figure here. Okay. So at the server, we have a frozen public pre-trained model. Remember, this is not trained on any hospital private data. Okay. Using the deep inversion algorithm, the server generates a synthetic data denoted by B. Here you can see. Okay. These images look similar to medical images but are artificially generated. Since they are synthetic, they do not reveal the identity or information of any real patient data. So the first step is simply creating a common synthetic data set for all clients. Second step you can see here is the distribution of the synthetic data set. So in step 2, the server distribute this generated data set B to every participating hospital. So the server is not sending a global model and it is not sending model parameters. Okay. It is only distributing a small synthetic data set that will later be used for knowledge transfer. Every client receives the same synthetic image in this model. Okay. Third step. So third step is private local data. Now let us, you can move to client side. Okay. So each hospital already has its own private data set. Okay. You know that hospital are having their own original images, which we are represented here as D1. Okay. So this is the actual patient data collected by the hospital. So the most important point in is that this data set always remain inside the hospital. Okay. It is never uploaded to the server or shared with any other client. This is the primary privacy guarantee of this framework. Okay. So now the step 4 is a shared data set B. So along with this private data set, that is the original data set of the hospital, each client also has the shared synthetic data set B from the server. Okay. So now every hospital, you can see which is referred to as client 1, has two data sets. Its own private public data set D1 and the common synthetic data set B. Okay. So the private data set is used for learning patient specific knowledge, while the synthetic data set acts as a common communication medium among all clients. Now, step 5 is a local model training. So in step 5, every hospital trains its local neural network denoted by F theta K. Okay. So the training is performed using hospital own private medical data. Since the training happens locally, sensitive patient information never leaves the hospital. Each client therefore develops expertise based on its own local data distribution. Now, step 6, moving to step 6. Okay. So Steps is now comes the biggest innovation of MediSec. So herein you can see this in step 6. After training, does the client send the model weights to the server? No. The answer is no. Instead, each hospital passed the shared synthetic dataset B through its trained model and compute predicted prediction logics represented as Z1 here. Okay. In- you can see in the figure here where number 6 is written. So these logics are simply the output scores before applying the softmax function. So only these logics are transmitted to the server. So just think about the difference first. In FedAVG, millions of medal parameters are uploaded. Here, only a few output value corresponding to the number of classes are uploaded. So this reduces communication cost. Now coming to step 7, logic aggregation at the server side. So now the server received logics from all participating hospitals. Instead of averaging a model parameter, it computes the average of these logics. So this produces the aggregated knowledge, Z average. Okay, you can see here. So you can notice here it is written no model weight shared. Okay. So this is the defining characteristics of MediSec-Fed. The server never receive neural network parameter. It only receives prediction information. Now the step 8 is a knowledge distillation. You can see here. So the server sends the aggregated logics, okay, uh, back to the hospital. Each client now perform knowledge distillation using KL divergence laws. So in simple words, you can say that every hospital learns from collective knowledge of all other hospitals while still preserving its local specialization. So after this update, the next communication round begins and the entire process repeats until the model converges. So if we summarize the entire workflow in one sentence, so the server generates synthetic data, hospital trains locally, hospital share only prediction logics, the server aggregate these logics, and every client learn from the aggregated knowledge through knowledge distillation. This is why MediSec Fed is much more secure than traditional federated learning because patient data never leaves the hospital, model parameters are never shared, only compact logics are exchanged, making the framework both privacy preserving and communication efficient. So moving to key contribution. So what is the novelty? How is this work is different from existing model? So basically contribution one first you can say is no model parameter sharing. So second step is you can say it is data free knowledge distillation. Robust malicious clients is also there. It is communication efficient. Okay. So like think about a deep learning model like ResNet 18. It contains approximately millions of trainable parameter and requiring around 44 MB of data to be transmitted in every communication round. But in MediSec-Fed, instead of sending millions of parameters, client sends only a few logic values corresponding to the output classes. Therefore, the communication requirement is reduced from megabytes to only a few kilobytes. Okay, this is the huge advantage, especially for hospitals connected through a slow or bandwidth limited networks. Other you can say like better privacy and security. Okay, since the model parameters are never transmitted, the possibility of server side model inversion attacks becomes extremely small. Also, it like supports heterogeneous models. Okay, so what is that? So another, you can say, knowledge is exchanged through logic rather than weights. So one hospital can use ResNet 18, other may use ResNet 14 or any other model. Okay, you and may use an entirely different CNN architecture. Despite using different model, they can still collaborate efficiently through knowledge distillation. So this is the flexibility not available in classical FAD-AVG. So coming to Medisec Fed versus Fed AVG, I already told you what is shared in Fed AVG. Full model weights and gradients are shared in Medisec Fed. Only output logics on synthetic set are shared. Data exchange per round. Suppose we are considering ResNet 18 in Fed AVG, it is around 44 MB, and in Medisec it will be around few KBs. Global model in terms of only shared model for all clients, and in Fed AVG, in Medisec client, each client keeps a personalized model. Then from server side model inversion attack risk, here in Fed AVG possible because server sees weights. In Medisec feed it is not possible because weight never leaves client. Then robustness to malicious clients. It degrades sharply. Even one bad client, a malicious client can hurt our complete architecture. And it learns well with 20 to 40% malicious clients also. And heterogeneous architectures are not supported, as I have already discussed. Like in Medisec we can use any different CNN, still model performs. Okay. So to conclude, Medisec Fed demonstrate that hospital can collaborate to train AI model without sharing either patient or model parameter. By combining model inversion and knowledge distillation, the framework provide better accuracy, lower communication cost, and improve robustness against malicious client, making it promising solution for privacy preserving medical artificial intelligence. Like any research work, there is still scope for improvement, such as generating more diverse synthetic data and evaluating the framework on larger medical data set. So the key takeaway is very simple from this work. Instead of sharing models, we share knowledge. With that, I conclude this presentation. Thank you very much for your attention. Sri Datta, you can continue now.
Thank you, sir.
Yeah.
Thank you, sir. We sincerely appreciate the time and effort you have devoted the sharing your knowledge, practical insights, and valuable experience.
Yeah.
So once again, uh, we extend our sincere gratitude to Dr. Abhinav Kumar for sharing his expertise with us. Thank you very much, sir.
Thank you, sir. Sri Datta, please continue.
Sure. Um, I'll share my screen. Thanks, sir, for the nice presentation. Uh, I'll begin with the next implementation, Fed average. Uh, so, Fed average momentum or Fed Adam. In this algorithm, the main overview is when there was like federated algorithm was being implemented. There was rounds after rounds. It did not depend on the previous update. What was thought of is as the update was done in the side of the central server, why not make it dependent on the previous update? So for that, an momentum style and Atom style uh, update was being configured. What was thought of is why not introduce empty as dependent on the parameters of beta 1 and beta 2. which is basically the first order and the second order momentum. And similarly was thought of for Fed Adam with the appropriate equation WT1 WT plus learning rate of the server and like what was the previous momentum upon the velocity. So now here the implementation is there. So what's the difference in the implementation is when the mode here. So in this function, it continues to be a similar as earlier. Only what we are going to do is we are going to introduce this uh, uh, like different modes. Mode in Fed average algorithm continues to have a pseudo gradient plus flat, and while mode of Fed average and Fed Adam was dependent on this momentum and velocity, and then whatever updated weights that we got, that is flattened weights, we unflattened it, and then we basically updated it in the hist list. So now we ran this algorithm with different modes, and then we tried to test out on the test set what are its output. And the clients that were being used is as non-IID clients. So when we run this, we will get a plot. So these are the plot. So the momentum actually has a oscillations in the learning, while the learning of Fed average and Fed Adam was quite uniform. Uh, but when it translates to the final accuracy actually made differing claims. Fed average final accuracy was 83.69. When we added momentum to it, just momentum would mean range of values from the previous gradient updates to control the momentum. It was 81.19, while Fed Adam showed a supreme performance of 85.88. So clearly making the updates dependent on previous uh, updates in a proper controlled scenario using like Adam optimizer will surely shoot up the accuracy. That was the finding here. And in the next one was the dynamic regularization. So in this, what was thought of is when we have this
Sorry,
Fed. Yes,
sorry to interrupt you, Sridatta. Can you
yes.
please it quickly because time is almost done 7:30. So quickly wrap up the content.
Okay, so, and then this will be the last, then we will uh, close. So coming on to the next part is dynamic regularization. So in this, what was thought of is uh, uh, a movement of or a collection of the control vector. Like if there is a certain client making a very higher like drift, and why not when it makes a drift, it actually differs from the previous or the server. So when the server weight is aggregated, uh, the server the performance of the server and the client will differ. So what was thought of is why not make this updates very smooth across the client by introducing this extra HT like memory vector and a regularizer using L2 now. So this was being applied, and the application was done in the rounds of the federated learning, and the application was done in this part where the weight updation is done, and then like when the alpha value is the hyperparameter here, as there is a updation of the memory vector as well. So when we run this, alpha is equals to 0 would be a normal fed average algorithm, and alpha is equals to 0.005 would be dynamic. So when we applied this, there was a decrease in the final accuracy of the central server, but again the drift was lesser in this case as compared to the non-application. So the client which had caused higher updates now has a uniform updates across. So yes, sir, that was all I had for the presentation.
Thank you, thank you, Sridatta,
Thank
for
you
a
so much.
nice demonstration.
Thank you, sir.
You wonderfully explain all the federated learning algorithm like fed average, fed prox. So all you did a wonderful job.
Thank you,
Okay,
sir.
thank you very much.
Thank you very much, sir. Thank you, sir.
Now, dear participants, if you have any doubts or if you have any query, you can please write in chat box. So, next 2 minutes we are available. If you are posting some your doubts, then we can solve your doubts. Else, we are ready to leave the meeting.
One more thing, sir. Like for future collaboration, like you can also drop the mail to Professor Abhinav sir and Professor Vandana ma'am. That was.
Sure, ma'am. I will inform them to if they want to connect with Professor Abhinav sir or Dr. Vandana Bharti ma'am. So I will share their email ID to all the participants. So if they are interested to collaboration with the IIT Roper and Abhinav sir and Vandana Bharti ma'am, so definitely they will interact there. Okay, so Sridatta, I think there is no question from the participant side, participation sides. So thank you very much to Sridatta. Okay, so now it's time is means done. Okay, so now we are stop the session here only.